Hello, this is the luckiest maths teacher in the world. Today we're looking at operations with surd. So just so we remember, a surd is the square root of a number, let's just call that a, where a is not a perfect square. So we're going to look at operations, which means adding, subtracting, multiplying, and dividing. So similar to fractions and I guess multiplying by algebraic terms, multiplying is a lot easier than adding or subtracting, so we're going to start with that. So, for multiplying, the rule is that the square root of a times the square root of b equals the square root of the products a and b. So, for example, square root of 5 times square root of 2 is exactly the same number as the square root of 10. So, the reason that this is true, what I just said about multiplying, is from one of the index laws we've already gone through. So we went through the index law that a times b to the power of m is the same as a to the m times b to the m. So for this down here, we're sort of doing it in reverse. We're starting with this and going there. So 5 is just the same, square root of 5 is the same as 5 to the power of a half. 2 is the same as 2 to the power of a half. So we can write that because they have the same power, we can start with something that looks like this and go to something that looks like this. So that would be 5 times 2 in brackets to the power of a half. And we know, of course, that 5 times 2 is 10, and something to the power of a half is a square root. So that's why it works. Now, division works in a similar way because division is just the opposite of multiplying. So, I'll actually just write the rule first. So the square root of a divided by the square root of b equals the square root of a divided by b. Okay? So as an example, square root of 20 divided by square root of 2 is just the square root of 20 divided by 2, which is root 10. Okay? And that's simply because division undoes multiplication. Square root of 20 divide 2 is just the same as square root of 20 times 1 over square root of 2, like that. And then we're just using the same rule that we used, okay? So dividing and multiplying is easy. So now we're going to look at how we simplify. So please copy this down if you'd like to keep it. So simplifying surds. Here we have simplifying, meaning the same thing that we do when we simplify fractions. So when we simplify a fraction like 12 over 20, what we want to do is we want to write that fraction in the same way. We want it to be the same number, but with smaller whole numbers. So 12 over 20, we can just, divide top and bottom by the highest common factor, which is 4, and write it simpler like that. It's the same for surds. What we want to do is we want to write the surd so that it's the same number, but we're using smaller whole numbers. Now, just like with fractions, you can't simplify every surd. So let's say we have something like the square root of 200. Now, to simplify that, we have to check, is the number in the square root, in this case 200, divisible by another square number? So we don't want to include 1 because that really doesn't help us. So if it is divisible by a square number other than 1, then we can simplify. So you have to know your square numbers for this. Now, just like when we were simplifying this fraction over here, when we divided by the highest common factor, here we want to find the highest square number that goes into it. So 200 is divisible by 4, for example. 4 is a square number other than 1, but it's also divisible by 100. So we want to pick the highest possible square. Now, because of what I said about multiplication, I can write square root of 200 as the square root of 100. So I chose 100 because it's a square number times the square root of 2, right? But square root of 100 is just 10, so I can write this as 10 root 2. So square root of 200 is exactly the same as 10 root 2, but now the number I have under the surd is smaller, so I've simplified it. So let's do a few other examples. So let's say we want to find out the square root of 50. Well, 50 is divisible by a square number. Again, you have to know your square numbers. It's divisible by 25. So I can write this as root 25 times square root of 2 because of the multiplicative property of surds. So square root of 25 is 5, and I can just leave the root 2 as it is. Let's look at the square root of 40, okay? That, again, is divisible by a square number, this time 4. So square root of 4 times square root of 10, because 4 times 10 equals 40, and then that equals 2 root 10. Okay, now let's look at the square number of 53, for example. Now, 53 is a prime number, so it cannot be divided by any other number other than itself and 1. So 53 is obviously not a square number, so we can't simplify it. So there's nothing we can do with that. But that doesn't only work for prime numbers. Sometimes numbers are not prime, but they're still not divisible by a square number. So, for example, let's see the number square root of 34. Now, 34 is not prime, obviously, but no square numbers other than 1 go into it. It's not divisible by 4, 9, 16, 25. The next one's too big anyway, 49. So, I can't simplify it. I just leave it as it is. Alright? So, simplifying is not just important to make things easy to understand, but we also need it in adding and subtracting surds, and that's what we will do now. So again, copy this down if you'd like to keep it. So when you're adding and subtracting surds, they're very similar to adding and subtracting algebraic terms. So you know, for example, if you had 2x plus y, you can't add them together because they're not like terms. It's the same for surds. So if I have, say, root 2 plus root 3, I can't add them together and make it a different surd, a simpler surd. Root 2 plus root 3, that's just the answer to the exact form. I could write it as a decimal, then it wouldn't be exact. But I can't make this any simpler than what it is. Okay? But if they are like terms, then I can. So let's say I have 2 root 7 plus root 7. So think of the root 7 like an x. I've got 2x plus x, I just add the coefficients. Again, if nothing's written in front of it, no number in front of the surds, it's the same as 1 in front of it. Root 7 is the same as 1 times root 7. So if you have 2 root 7s and you add another root 7, you have 3 root 7s. Similarly for subtracting, so let's say I had 3 root 15 minus 4 root 15, exactly the same thing. You operate on the coefficients, so 3 minus 4 is negative 1, and you keep the surd as it is. Okay? Now the thing that makes this a little more complicated than adding or subtracting algebraic terms is what I just went through, simplifying. So let's say I have a question like this. So let's have something like root 48 plus root 27. Now they're not like surds, so I can't just add them together. But if I simplify them, I will be able to add together. So square root of 48 is the square root of 16 times the square root of 3. And root 27, simplifying again, root 9 times root 3. Again, I chose 9 here and 16 here because they are square numbers. So 48 and 27 are indeed divisible by square numbers. So let's simplify the first one. So square root of 16 is 4. So root 48 is the same as 4 root 3. But root 27 is 3 root 3. So I can actually add them together now. This root 48 plus root 27 is just 4 root 3 plus 3 root 3, which is 7 root 3. So what you will need to do when you have unlike surds is first check whether they can be simplified in such a way that you can add them together, just like I did there. Other than that, we just add together or subtract as well, like surds. Hope you enjoyed the video. This has been the luckiest maths teacher in the world. Have a great day.